Hello and welcome to another video with me. I want to say thank you for stopping by and coming to listen to my explanations of calculus. We are now on to topic 2.3, rules of limits. So the first rule of limits that I just want to go over is the limit as x approaches a of f of x plus or minus g of x is equal to the limit as x approaches a of x of f of x plus or minus the limit as x approaches a of g of x. And you'll see that I have some practice problems written out where we're going to work through a lot of these. So let's real quickly work through the first one. And I have a graph of f and g of x that we're going to use. As x approaches -4, it looks to approach this point of like -3 for f of x. Let's see, yeah, it approaches -3, and it also approaches -3. So we're quickly just breaking down this limit to make it a bit easier, and we are going to use white to work this. The limit as x approaches a of f of x plus the limit as x approaches a of g of x. So we know that this is going to approach -3. And we know this limit here, g of x, well, once again, it's seemingly approaching this value of -3 from the left, or from the right. And it looks to approach that value -3 from the left, so that's also -3. Add them together, and we get -6. Alright, let's erase that. And continue on. I just want this -6 part. There we go. Alright, continuing on to our next limit rule, or our next two limit rules that we need. It's going to be the limit as x approaches a of a constant times by a function f of x is equal to said constant times by the limit of the function of f of x. So really, if you took the limit of g of x here, or the limit as x approaches 3 times g of x, then it's going to just be 3 times the limit of g of x. Alright, continuing on, we also have the limit as x approaches a of a function times by a function is equal to the limit of the first function times by the limit of the second function, which is also just technically invertible if you so wish. So, using these two rules, we are now going to solve this bottom limit. I'm going to pull out this 5, so we get 5 times the limit as x approaches 1 of f of x times by the limit as x approaches 1 of g of x. Well, the limit as x approaches 1 of f of x, well, f of x is this green function up here, and it looks to approach the value of 3. So this is 5 times by 3. G of x, on the other hand, it looks to approach this value of -5. So it's just -5. So we get a value of -75. Alright. Let's erase. And continue on. Okay. The last limit rule that we have is the limit as of a rational function, so f of x over g of x is equal to the limit as x approaches a of f of x over the limit as x approaches a of g of x. So, looking at this final problem, we can break this down into Really, this is just negative 1/2. Negative 1/2. So we're just going to call this negative limit of g of x as x approaches 3 over 2 limit as x approaches 3 of f of x. So g of x, we're looking at the function in blue, and we're looking at it at x is equal to 3. That looks to be a value of 2. So g of x is going to be equal to negative, or is going to be equal to negative 2. The limit as x approaches 3 is 2, times that by negative 1 is negative 2, over 2 times by the limit as x approaches 3 of f of x. Well, f of x at 3 looks to approach 5. So then we will have 2 times 5. The 2's will cancel, so we just get really negative 1/5. Alright, continuing on. We have a few more limit rules. So we have the limit as x approaches a of f of x to the power of n is the same thing as the limit as x approaches f of x to the power of n. The limit as x approaches a of the square or the nth root of f of x is the same thing as the nth root of the limit as x approaches a of f of x. The limit as x approaches a of a constant is just equal to the constant. The limit as x approaches a of x is equal to a. The limit as x approaches a of x to an n power is equal to a to the n. And finally, the limit as x approaches a of the nth root of x is just equal to the nth root of a. So I want to use these now to solve this problem that I've given us. So, starting out with I, we have the limit as x approaches 1 of h of x to the negative 3. Well, we are going to call this the limit as x approaches 1 of h of x raised to the negative 3rd power. H of x at 1 is just negative 1. So this is really just the same thing as negative 1 to the negative 3rd power, which is 1 over negative 1 to the 3rd. So it's really just equal to negative 1. Alright. Gotta get rid of that. Continuing on. Well, let's write out the answer real quick. So we get negative 1. Continuing on, we have I, or 2. We want to know the limit as x approaches 2 of h of x. That's actually a pretty easy one. And this is just using the rules of like direct substitution that we've shown. Well, we're going to go over to 2, go all the way down, and in fact, it's supposed to be at 8. It's kind of not centered, but it's supposed to be at 8. So we approach 8 from the bottom and from the top and the bottom. So it looks to be negative 8. Not negative infinity, negative 8. Alright. This one I kind of did a little trick, because a function divided by itself, no matter its value, is always going to be equal to the limit as, or is always going to be equal to 1. So, we will get this limit as x approaches negative 2 of 1. Well, we know that a limit as x approaches something of a constant is just a constant, so that's equal to 1. So this last one, I kind of want to incorporate a small bit from yesterday. We're going to do the limit as x approaches -1 from the left of 3h of x. Well, we are going to first start out by pulling out this 3. So we get 3 times by the limit as x approaches -1 from the left of h of x. And this allows us to then solve this limit right here. Well, if we're looking at it coming from the left, we're going to see that once again it just approaches +1. So this is going to be 3 times by 1, or it's going to be equal to 3. Alright, continuing on. We have direct substitution. Now, direct substitution is not always going to work, but there's several ways that we can make it work. So if f is a continuous function and a is in the domain of f, then the limit as x approaches a of f of x is equal to f of a. What is a continuous function, you might ask? Well, you're going to find out here in a few videos. But for right now, the way that I would like to define it is a function that you can draw without your pencil leaving the paper. Anyway, I digress. So, there's several ways that we can find these limits. And sometimes it might involve multiplying by a conjugate, getting common denominators, factoring. Sadly, I don't have a conjugate one here, but that's fine. I think with our work with the difference quotient, we'll get enough practice with that. Alright, so to start out with this first one. Well, if I plug in 2 into this denominator is going to go to 0, which makes this undefined. So, we're going to try doing something different. We're going to factor it. So, we are going to get, and then, what's it called? I'm going to show you the box and diamond method. So, we have an x. We're going to put the middle value in the top. And we are going to put the multiple of the outsides in the bottom. So, we're going to get -2. And we want to know what two functions are going to multiply to -1, or sorry, add to -1. I did this wrong. And multiply to -2. Or multiply to negative. Nope, give me one moment. So we're looking for two numbers that are going to multiply to get this bottom number, but add to get this top number. So I think the candidate that we are going to want to choose is -2 and 1. Then we're going to put this into a box where we're going to have a -2x and a 1x and x squared. Sorry, this needs an x squared. Oh, that would have been easy. Forget it now. And then a -2. That explains why I was getting so confused, though. So we're going to find whatever needs to be on the outside of this box for us to factor it. So we're going to get an x and an x, a 1, because x times 1 is 1x, and then a -2. And these are our factors, x minus 2, x plus 1, and x minus 2. Alright, so now we can cancel, and we are left with the expression of x plus 1. Note that this is not defined at x is equal to 2, but because we're taking the limit as x approaches 2 and it's continuous, it's still going to be equal to the limit. So we can just plug in 2, and we get 3 for a limit. That worked out really nicely. Let's do another. We got another one where it involves a lot of factoring. So let's start by factoring this numerator. So we get an x times by x plus 3. And that's where one of our issues takes place. This numerator is going to go to 0. Over, well, once again, we can use our box and diamond. So we want to put the middle term, which is this -1 in the top, and this whatever these two bottom other terms multiply to in the bottom, so -12. Okay, so we're going to look for a number that adds to -1 and then multiplies to -12. So we have multiple candidates, but I think the right one's -4 and 3. And what you'll notice is if there is no coefficient of x squared, you don't have to put it in the box. So what we would get is x minus 4 and x plus 3. And this x plus 3 is going to cancel out, leaving us with the expression of x over x minus 4. As this approaches -3, this numerator is going to approach -3. As we know, the limit of a rational, so this is just really the limit as x approaches -3. And down here is also the limit as x approaches -3. Over, well, as x approaches -3 in the denominator, that's going to approach -7, so we get 3/7. Alright, this last one is incredibly challenging. And you're going to find very soon that this represents one of two very key concepts of calculus. But you don't know what that concept is just yet. Well, maybe you do. So we have the limit as h approaches 0 of 1 over h, I'm going to call it, times by 1 over x plus h squared minus 1 over x squared. How can we evaluate this limit? Well, let's find a common denominator first. Let's see if we can do anything with that. So multiplying through, cross multiplying, so we're going to get an limit as h approaches 0 of 1 over h times by x squared divided by x squared times by x plus h squared minus, and this is going to be x plus h squared minus x squared over x squared times by x plus h squared. Well, I think what I want to do with this is expand out the numerator, not the denominator, specifically just the numerator. So we are going to get the limit as h approaches 0 of 1 over h. And I'm also going to combine this. So we're going to get an x squared minus, well, x times x is x squared. We are going to get minus 2xh minus h squared all over x squared x plus h squared. Well, looks like I'm about to run out of space, so give me one. Okay, now that I have a bit more space, let's now see what terms cancel. So we get a limit as h approaches 0 of 1 over h. This x squared and that x squared will cancel because it's x squared minus x squared. And let's factor out an h. So we get 2x minus h all over x squared times by x plus h squared. And this h and this h will now cancel. So we now have the limit as h approaches 0 of 2x minus h over x squared times by x plus h squared. Let's now break down this limit into its rational components. So we are going to get the limit as h approaches 0 of 2x minus h divided by the limit as h approaches 0 of x squared times by x plus h squared. Alright. Well, let's look at this numerator first. This is going to just approach 2x, as we can just direct substitute in h for 0 for h. And in this denominator, once again, this is going to look to go to, let's see, give me one moment. Alright, this bottom is going to go to x to the 4th. And these x's will cancel, so we're just left with 2 over x cubed. That, my friends, is our final answer. Now, I have one last thing for us to do today. And it's kind of dealing with a theorem in calculus. This is a somewhat important one to know, as it's used in several proofs. But it basically goes as such, and this first theorem is not the squeeze theorem, but it's highly related. If f of x is less than g of x when x is close to a, and the limit of f and g exists as x approaches a, then the limit as f of x is less than the limit of, or equal to the limit of as x approaches a of g of x. So just giving you a small bit of like an example, if I were to sketch a graph, and I have this function g of x, which we're going to define, and we have this function f of x. If f of x is always smaller than g of x, at least close to a, and let's say our a here is 0, then it must always be less than or equal to the limit. If you understand what I'm saying. Sorry. But, continuing on, the squeeze theorem is basically supposing that we have 3 functions, and g of x is sitting in the middle. It's kind of like a sandwich. And all 3 of these limits exist, then if f of x is less than or equal to g of x is less than or equal to h of x near x, or near a, sorry, and the limit as x approaches a of f of x is equal to the limit as x approaches g of x, well then the limit of h of x must be equal to L, because this value of f of x is really just equal to L. And so it must be less than or equal to L, at the very least. And continuing on, this h of x is also equal to L. And then solving this system of this inequality will only give us L is equal to g of x. It has to be L, because there's no numbers in between L and L. Alright, continuing on, I have one squeeze theorem problem I'd like to do. And this problem, I want you to think about it for just a moment. Okay, now that you've thought about it, hopefully, how would we show that the limit as x approaches 0 of x squared of cosine of 20 pi x is equal to 0? Well, of course, x squared goes to 0. But how do we show that? How do we show that this function is going to be equal to 0 at 0? Well, we can take 2 functions, and in fact, there's this function inside of it that's going to dictate what we could maybe use, this x squared. So let's say that f of x is equal to x squared. And our h of x, h of x, I want to find the upward bound first. And our f of x is equal to our negative x squared. And you might be wondering, why did I choose negative x squared? It's because sometimes this cosine value is going to make this function negative. So, it's important for us to have bounds on both sides. That's going to encapsulate this. So what this function is really going to look like is, I'll do this in orange for this x squared of cosine of 20 like pi. What this function is going to look like is way out here there's going to be very big squirrels, but as soon as you get close to this origin, it's going to go crazy, and then it's going to go back to being big. But we can line up these parabolas, and sorry, my drawing here does not reflect this, to kind of squeeze, because we know that no matter what, the maximum value of this function is going to be defined by this parabola. This cosine of x is going to either be equal to 1 or less than 1, so it's going to always be smaller than the parabola. So this x squared is always going to be the defining of like the largest number. Alright, so we now have our functions. Let's show that the limit for these two functions approaches L, so then we can show that this limit is going to approach L. Well, if we take the limit as x approaches 0 of h of x, it will approach 0 using direct substitution. The limit as x approaches 0 of f of x is also equal to 0 using direct substitution. If we know we have this value L for this function that is going to lie entirely in between these other two functions, we know that L must be equal to 0, as thus showing that this x squared, a cosine of 20 pi x, is equal to 0. Well, I hope you all found this video informative and enjoyed. I hope you all have a wonderful rest of your day. Bye-bye.